Hello. So this time we consider this problem of finding conditions associated with differentiability. So we have here a piecewise defined function, and we would like to know for which values of a and b is that this function represents a differentiable one. Well, let's start. First thing is to note uh, that we have two unknowns, namely a and b. So we may need two non-equivalent relations among these quantities a and b to determine them. Now, where is that these conditions are going to come from? Well, we require differentiability, right? But for a function to be differentiable, it has to be continuous. So that's going to be our first source of a relation, that of continuity. So let me put it in these terms. For a function to be differentiable, it has to be continuous. And for it to be continuous, the following equation should be satisfied. So for each number c, the limit, number in the domain, of course, of the function, the limit as x tends to c of f of x should be f of c, right? In particular, we should have that the limit as x tends to 0 of f of x must be f evaluated at 0. But let's translate this equation that we have here. If you recall from the times of discussions about limits, for a limit to exist, it suffices, or it's actually equivalent to indicate that the two-sided limits are actually equal and existential, right? So I can transform this equation into the following. We would say that the limit as x tends to 0 from the right of f of x is the same as the limit as x tends to 0 from the left of f of x, and these two limits should be equal to the function evaluated there, right, at 0. Of course, I'm going to translate this in the following terms. I'm going to say that this is the limit as x tends to 0 from the right of sine of x. Why from the right? Well, as we can see from the definition, right, as we are approaching to 0 from the right, we're taking values that are, well, larger than 0 in order to approximate it. So this is the proper expression to use in that approximation process. Now, something similar is going to occur on the left. So I'm going to say the limit as x tends to 0 from the left of ax plus b, because now we're taking values that are less than 0 in order to approximate our function, but the one that we're going to be using is this expression at the bottom, the linear one. And in turn, all of them should be equal to the sine of 0. Of course, the equation that we have here, we know that sine is a continuous function. We know that a linear expression is a continuous function. So we just evaluate directly. This says that the sine of 0 is equal to a times 0 plus b, which in turn, well, is equal to 0, because that is the sine of 0. But then you say, well, look, this is redundant. These two are equal. But this equation imposes a condition on b. So b must be 0. Okay, so now we have our first relation here. For the second portion, let's use the concept of differentiability. No? We use that of continuity. So what does this mean in our context? Well, we will say this. The derivative must exist everywhere. In particular, the function should be differentiable at 0. But how do we translate this into equations? Well, first, we have that the limit as h tends to 0 of the expression f of 0 plus h minus f of 0 over h should exist. And it should exist, and it should be equal to its left-sided limit and its right-sided limit at the same time. In other words, I can translate this in the following terms. I'm going to say first that the limit as h tends to 0 from the right of f of 0 plus h minus f of 0 over h, well, this should be equal to the limit as h tends to 0 from the right of sine of 0 plus h minus sine of 0 over h. But this is nothing else but the derivative with respect to x of sine of x, right, evaluated at x equal to 0, which is nothing else but the cosine evaluated at 0, which is 1. The second indicates that the limit as h tends to 0 from the left of the same expression as the one above should be equal, right, to the limit as h tends to 0 from the left of, well, let's see, what should be this? We're taking smaller values approaching from the left, so we should use this expression, and this one should be a times 0 plus h plus 0, because now we unveiled that b is 0, minus the sine of 0, which is the actual value, right, of the function at 0, over h. But then, well, what happens? This says that this better be the limit as h tends to 0 from the left of a times h divided by h, which is nothing else but a itself. So this says, since this limit that I'm underlying here, right, that I'm boxing here, should be equal to either of these two, right, to any of those two, we should have that a is equal to 1. So for the function to be differentiable, we should have the following. It should be sine of x if x is greater or equal than 0, and it should be 1 times x plus 0 if x is less than 0. And with this we finish. I hope that you like it. Take care and subscribe.